Hello, in this video we are going to discuss limiting reactants and percent yield. So when we're cooking, we are likely going to run out of one ingredient first. And that ingredient that runs out first is called the limiting reactant. And it's going to limit the amount of product that forms, or whatever we're baking. So for example, let's say we're making a peanut butter and jelly sandwich, and our recipe calls for 2 tablespoons of peanut butter and 1 tablespoon of jam to make one sandwich. Of course, we're ignoring the bread here. What if we have 5 tablespoons of peanut butter and 2 tablespoons of jam? So that's just what we have around the house. How many sandwiches can we make according to our recipe? So it looks like, we have 5 tablespoons of peanut butter and we need 2 tablespoons for every sandwich. So that would give us 2 sandwiches with 1 tablespoon of peanut butter left over. And then looking at the jam, we have 2 tablespoons of jam. We need 1 tablespoon for every sandwich. So that would also give us 2 sandwiches. So which ingredient ran out first? Or another way of asking that question, which ingredient limited the amount of sandwiches we could make? Well, in this case, the jam ran out first. We used all of the jam in our 2 sandwiches, so the jam is the limiting reactant. And then the peanut butter, we did have 1 tablespoon left over of the peanut butter. Okay, so let's talk about this more in terms of chemistry. So let's say we have A reacting with 2 B's to produce 3 C's. Let's say that's our chemical equation. We want to make sure to balance it first. We want to have correct coefficients for each reactant and product, because in the next step, we're going to convert any given information into moles if it's not already in moles. So very similar to what we did in the last video, we want to make sure to convert what we have into moles. And in order to do that, we need the correct coefficients. So we need a balanced equation. And then in the next step, we're going to use stoichiometry or mole ratios for each reactant to find the mass of product that's produced. So for example, let's say we're told we have 5 grams of A and maybe 4 grams of B. So we're going to convert each into moles first, and then we're going to convert that into moles of the product C. So we'll do that for each reactant. And then if we want, we can go one step further and convert that into grams of our product. Now, once we have grams of our product that's produced from each reactant, assuming we use all of the reactant, then we go on to the next part. So the reactant that produces a lesser amount of product is the limiting reactant, or the reagent, sometimes we say. And then the reactant that produces a larger amount of product is the excess reagent. So very similar to our jam and peanut butter. One ran out first and one had a little bit of extra left over. All right, so let's look at an actual problem, see how this works. So we're going to consider our sodium and chlorine reaction again. So 2 sodiums plus 1 chlorine produces 2 sodium chlorides. And if a chemist starts with 5.2 moles of sodium and 3.2 moles of chlorine, which reactant limits the amount of product? Okay, so we're given information about both reactants. So we want to first convert moles of sodium. So we're kind of in the middle of our flow chart. We already have moles, so we just want to convert moles of our reactant to moles of our product. And we'll do the same for chlorine. We'll convert that to moles of product. And then we're going to compare those amounts for each reactant and see which one produces a smaller amount of sodium chloride. And that's going to tell us that that reactant runs out first, because we can only make as much product as reactant that we have, right? So we can't make more product than what we have. All right, so let's start with sodium. So we're going to convert 5.2 moles of sodium into moles of our product. So for this first one, we're just focused on sodium and the product, and it looks like there's a 2-to-2 ratio. So essentially 1-to-1. Now, what do we want to put in the numerator? What are we solving for? Are we solving for sodium or sodium chloride? We're trying to solve for sodium chloride, right? We're trying to do this conversion up here. So let's put 2 moles of NaCl in the numerator and 2 moles of sodium in the denominator. Now, obviously the 2's cancel, moles of sodium cancel, and we just get the same number back. We get 5.2 moles of sodium chloride. All right, so now let's do the same thing with chlorine. So we were given 3.2 moles of chlorine. And this time, we're just interested in chlorine and sodium chloride. So it looks like there's a 1-to-2 ratio. So again, we're solving for sodium chloride, so we'll put that in the numerator. And we'll put 1 mole of Cl2 in the denominator. Okay, so moles of chlorine will cancel, which will give us a unit of moles of sodium chloride. And looking at the math, we're just multiplying 3.2 by 2. So we get 6.4 moles of sodium chloride. All right, so now we're going to compare the amounts for each product and which one gives us the smaller amount. Sodium. Okay, so we get that sodium is going to run out first. So this tells us that since the amount of sodium we're given produces a smaller amount of product, that means it's going to run out first. So sodium is the limiting reactant. Now, the other nice thing about this calculation is now we know how much product to expect. If everything goes 100% accurately and well during lab, which of course it never does, so we would expect to form 5.2 moles of sodium chloride in our reaction. So that brings us to a value that chemists have to calculate a lot, which is percent yield. So just like I said before, reactions are never perfect in the lab. You might spill a little bit of something as you're transferring from one piece of glassware to another, or sometimes a reaction won't completely finish because we just didn't put enough time or heat into it. So in order to assess the outcome of a reaction, we calculate something called the percent yield. How much of the product did we actually form compared to what we could have theoretically formed? So you can see the equation down below for percent yield. So this is equal to an actual yield divided by something called a theoretical yield, and then we multiply that ratio by 100. So let's talk about what those terms mean. So the actual yield in the numerator is the amount of product that you actually produce in the lab when you perform your experiment. And then the theoretical yield in the denominator is the amount of product that could form if everything goes 100% right, which of course very rarely happens. And the theoretical yield is calculated. So for example, in the problem we did earlier, we saw that we could form 5.2 moles of sodium chloride if everything went 100% perfectly. But maybe we get to lab, we do the lab, and we only get 4 moles of sodium chloride. We could then plug that into our equation here and get a percent yield. So let's do an example. So just like I said before, the theoretical yield must be calculated. And in order to calculate the theoretical yield, we have to identify the limiting reactant. So looking again at our sodium and chlorine example, sodium, we're told, is the limiting reactant. So let's say we start with 3.4 grams of sodium. So that's what we're given. How many grams of the product could form theoretically? So that would be our theoretical yield. All right, so we're given grams of sodium, which means we first need to convert that to moles. So always go to moles. Now, earlier we saw that we do need to convert this into the amount of product in order to get the theoretical yield. So we're going to convert this to moles of sodium chloride, and then we're specifically asked how many grams of product would form. So we need to also convert this to grams of sodium chloride. All right, so instead of doing this in steps like I did in the last video, I'm going to show what it looks like when we just set up each of our conversion factors side by side. So I'm going to start with what I'm given, 3.4 grams of sodium. And the first thing I want to do is convert that into moles of sodium. So in our last video, we saw that the molar mass of sodium is 22.99 grams per mole. Now in this first step, we want to convert this into moles. So I'll put 1 mole of sodium in the numerator and 22.99 grams of sodium in the denominator. Now, instead of just calculating this first step, I'm actually going to put the next conversion factor into my equation. And in this next step, let's see, so actually in this first step, we canceled grams of sodium. So now we're left with moles of sodium. So in this next conversion factor, we want to convert moles of sodium into moles of sodium chloride. And that's where our stoichiometry or mole ratios come in. So there's a 2-to-2 ratio here, and we're solving for sodium chloride. So 2 moles of sodium chloride will go in the numerator, and 2 moles of sodium will go in the denominator. And again, We're setting this up so that units will cancel as we go along. Now, instead of solving for this step, we're just going to keep going and add in our next conversion factor. So now that we have moles of sodium chloride, we're going to convert that into grams. So in the previous video, we saw that the molar mass of sodium chloride is 58.44 grams per mole. Now this time, we're putting the grams in the numerator. Oh, whoops, that should be 58, because we want to convert to grams of sodium chloride. And we're going to cancel moles of sodium chloride. Okay, so let's simplify the math. So it looks like if we go across the top, we have 3.4 times 1. I'm just going to leave the 1 out because that just gives us the same answer back. And then next we're multiplying that by 2, and then by 58.44. In the denominators, we have 22.99 times 2, and then times 1. So again, I won't include the 1, we can just skip that. And then our final unit is grams of sodium chloride. Now, if we plug all of this into our calculator, we should get a value of 8.6 grams of sodium chloride. Now, if you got a different answer, go back and make sure to put parentheses around your denominator values, because sometimes the calculator will think that you're just multiplying everything by 2 at the end. So you want to make sure to put parentheses around everything in the denominator, just so your calculator knows to divide by everything in the denominator. All right, so 8.6, we have 2 sig figs because we started with 2 sig figs in our given value. And this is our theoretical yield. So this is how much sodium chloride we could theoretically make if everything goes 100% perfectly. Now on the next slide, let's say you perform the actual reaction between sodium and chlorine, and then you weigh your product, and you find that the mass of sodium chloride from your experiment is 5.62 grams. So that would be your actual yield, the amount you actually made. So let's calculate the percent yield. So we're going to plug in our actual yield and divide that by the theoretical yield, which we just calculated as 8.6 grams, and then we're going to multiply by 100. So notice that grams will cancel, and we're just going to get a percentage. So I get 65% for my actual, percent yield. So we only formed 65% of what we were expecting to form, but in chemistry, that's actually a pretty decent amount. Because again, a lot of reactions don't go all the way to 100% yield. And this could just be due to various factors, just imperfections in the experiment, or maybe there wasn't enough heat or enough time to complete the reaction. Okay. Let's do one more problem. Oh no, the reaction didn't show up on this slide. I'll rewrite it down below here. So C6H12O6, which is glucose, is reacting with 6 moles of oxygen to produce 6 moles of CO2 and 6 moles of H2O. Yeah, I'm not sure why the equation didn't show up. I'll have to double check my slides later. But let's say that we start with 7.4 grams of glucose and we let it react with excess oxygen in the air. So what does that mean? This tells us that glucose is our limiting reactant because we're told that we have excess oxygen. All right, so glucose is going to limit how much product we can form. Now, let's say we perform the experiment and the actual yield of water is 2.3 grams. What is the percent yield? Okay, so we're given the actual yield, but we don't have the theoretical yield yet. So in order to do that, we need to start with what we were given, which was 7.4 grams of glucose. And we're going to, again, follow that flow chart from the last video. We're going to convert that to moles of glucose. And then in this problem, it sounds like the product we're interested in is water, H2O. So let's convert moles of glucose to moles of water, and then finally grams of water. Okay, so let's start at the beginning with what we're given. And it looks like we need to figure out the molar mass of glucose in order to convert from grams to moles. So pause the video, see if you can figure out the molar mass of glucose, and when you're done, we'll go over it together. Okay, so the mass that I got was 180.16 grams of glucose for every 1 mole. So again, here we're converting grams to moles, so I'm going to put 1 mole of glucose in the numerator and 180.16 grams in the denominator. Oops, glucose. And then in the next step, let's see, so we're canceling grams of glucose and we're left with moles. So now we're going to convert moles of glucose into moles of H2O. And it looks like there's a 1:6 ratio. We're just not shown that 1 at the beginning, but it's a 1:6 ratio. And we're solving for water. So let's put 6 moles of water in the numerator and 1 mole of glucose in the denominator. So now we're canceling moles of glucose and we're given moles of water. And then in the next step, we want to convert moles of water into grams. So we need the molar mass of water. So see if you can calculate the molar mass of H2O. All right, so the amount I got was 18.02 grams for every 1 mole of water. Now again, this time we're converting 2 grams, so I'm going to put the mass in the top of my conversion factor and 1 mole in the bottom. Okay, so putting it all together, we've got 7.4 times 1 times 6 times 18.02, and then we're dividing by 180.16, and that will give us the grams of H2O that theoretically could form if everything goes well. So if you plug this into your calculator, you should get about 4.4 grams of water. And I kept this to 2 sig figs because that's how many we were given. And again, this is our theoretical yield. So this is how much we could potentially form. All right, so let's plug this into our equation for the percent yield, which I've run out of room. So I'm just going to, let's see, let me just put a new slide in here. And remember, the equation for percent yield is equal to the actual yield over the theoretical yield times 100. So on the last slide, we were told that the actual yield is 2.3 grams of water. And we just calculated the theoretical yield as 4.4 grams of water. So then we'll multiply that by 100. So plug this into your calculator, see what you get. So I got 52% as my yield, which sounds awful, right? That's only half of what we theoretically could have made. But again, in chemistry, that's actually not a bad number. That's actually pretty good. So it's all relative, right? Okay, so hopefully this helped a little bit with understanding uh, limiting reactants, the fact that one ingredient is going to run out first, and that's going to limit how much product we can make. Additionally, that amount is our theoretical yield, so how much we could potentially make. And in lab, we never actually get 100% yield. It's very, very rare. Something always goes wrong. So then we can calculate this percent yield to figure out how well we did at our reaction. All right, so that's it for chapter 6, and I will see you in chapter 7.